Hello, this is Brianna. In this video, I will be talking about parametric equations. This is an example of a projectile being shot from a cannon. My x function is equal to parentheses v cosine theta and parentheses times t, and my y function is parentheses v sine theta and parentheses times t, subtracted by 5t squared. First, I'd like to show you my window. I chose my window based on certain points I got by plugging certain degrees into the parametric equations. Theta will be 15 degrees, 45 degrees, and 60 degrees. I was asked to find the length of the time the projectile was in the air, and that will be my t value. I got 5.18 seconds for 15 degrees, 14.14 seconds for 45 degrees, and 17.32 seconds for 60 degrees. My greatest length of time was 17.32 seconds, so for my T max I chose 20 to make sure everything was included in the screen. I was also asked to find the range of the projectile. I got 500 meters for 15 degrees, 1,000 meters for 45 degrees, and 866 meters for 60 degrees. My greatest value was 1,000 meters. The range is going to be a horizontal value, which is going to be my x. So for my x max, I chose 1,010. I was also asked to find the maximum height of the projectile. For 15 degrees, I got 33.5 meters. For 45 degrees, I got 250 meters. And for 60 degrees, I got 375 meters. My greatest value was 375, and height is going to be my y value. So for my y-max, I chose 400. Now to get the length of the time the projectile was in the air, I set the y function equal to 0 and solved for t, and got t equals v sine theta over 5, and I plugged in 15 degrees, 45 degrees, and 60 degrees in for theta, and substituted 100 meters per second in for v to get the values. For the range of the projectile, I set the y function and I substituted t for the x function of t. And so when I solve for t in the x function, I get t equals x over v cosine theta, and I plug that into that t into the y equation, set that equal to 0, and I get x equals v squared sine 2 theta all over 10, and I plug in the theta values in at 15 degrees, 45 degrees, and 60 degrees to get my range of the projectile. For my maximum height of the projectile, I set the y function and I take the derivative of that to get the maximum height, and then I set that equal to 0 and solve for t, and I get t equals v sine theta over 10, and I plug in 15 degrees, 45 degrees, and 60 degrees to get the time that it's at the maximum height. Once I get those values, I plug them back in to the original y equation to get the actual value at that time, which will be the maximum height. Now let's take a look at my functions. For my y values, I use the original y function that I was given, and correspondingly for my x. For this, I was given that v is equal to 100 meters per second, so I plugged in 100. And then as cosine of theta, I used 15, 45, and 60 for my thetas. And I plugged everything in correspondingly for the y values as well. So y1 and x1 will both have the same theta. Alright, now let's look at the graph of the functions. And you'll see the 15 degrees on the bottom, the 45 degrees in the middle, and the 60 degrees on top. The range of the projectile for 15 degrees will be 500, so it should stop first. The range for 45 degrees was 1,000 meters, so it should go the farthest. And the range for 60 degrees was 866 meters, so it should stop right in between. We can also see the maximum height of the projectiles. For 15 degrees, it's only 33.5 meters, which is about right there. For 45 degrees, it is 250 meters, which is right there. And for 60 degrees, it's 375 meters, which is right here. Now that the functions are done graphing, we can look at the length of the time that the projectile was in the air by tracing the graph. You can see it There we are. We're chasing 60 degrees. So the length of time the projectile is in the air was 17.32 seconds. So when I get to the end of the function in the far right bottom hand corner, t right here should equal 17.32. Alright, we're getting close to the end here. And we can see behind the numbers that it's about at the end, and it's 17.2. Which is what we calculated by plugging theta into the function. Now by looking at the graph, we can see that 45 degrees right here gives us the greatest range. It ends the farthest. It's nice to see it visually. 15 degrees is a low shot and it hits the ground very quickly. 60 degrees is too high, so most of the momentum is pushed up instead of out, so it goes up and then down and drops shorter than 45 degrees. 45 degrees is right halfway in between 0 degrees and 90 degrees, so it makes sense that it would be the optimal or the greatest range. We're all set. I hope this video helped with your understanding of parametric equations and how to use the given functions to solve for specific values.